Hey guys, welcome to lesson 9.3 on Arithmetic Series. Let's go ahead and start with some vocabulary. So first up on the agenda, we have the sum of the terms of a sequence is called a series. All right, so basically we have two separate words here that we need to talk about. The first word is a sequence, and as you know, we have such thing as arithmetic sequences, geometric sequences, and all that. So a sequence is basically just a collection of numbers that does or does not follow some pattern. Now, the sum of the numbers in a sequence is referred to as a series. So for example, the series 3 plus 6 plus 9 plus 12 plus 15 corresponds to the sequence 3, 6, 9, 12, and 15. The sum of this series, if you add all of those numbers together, is going to give you 45. So again, a sequence is a collection of numbers. A series is those numbers added together, or the sum of that sequence. So next up, we have an infinite series. Okay, so an infinite series is basically a series that has infinitely many terms. For example, we might have a series that looks something like this. 2 plus 5 plus 8 plus 11 plus 14, and then we see these little ellipses. And what that does is that tells us, hey, this is going on forever. This is an infinite series. Next word, we have any series whose terms form an arithmetic sequence is known as an arithmetic series. And that is the bulk of today's lesson, is discussing arithmetic series. So for example, if we have 1 plus 5 plus 9 plus 13 plus 17 plus 21, that is an arithmetic series with 6 terms. And the reason it's arithmetic is, well, to get from one term to the next, we are adding the same number. We continuously add 4, and since we have that common difference of 4, that means we're referring to an arithmetic series. All right, next term on the agenda for today is summation notation. Summation notation. I like that term, it's catchy. All right, so summation notation is the sum of all terms of the sequence denoted as this funky symbol, which is the sigma symbol, k equals 1 on the bottom, and n on the top. Then on the right-hand side, we have some formula a sub k, where k is the summation of notation. Okay, so obviously that's a lot to unpack, so let's look at an example and we'll talk about how this works. So if I had, for example, the summation notation that looks something like this, we have our sigma symbol. On the bottom of the symbol, I have n equals 1, and on the top, I have 5. Then I have the formula 3n minus 2. Well, let's talk about what this represents here. This is another way of writing the sum of some sequence, okay? N equals 1 is referred to as your lower limit. 5 is referred to as your upper limit. Now, what this means is the first thing you're going to plug into the formula, 3n minus 2, is the number 1. The last thing you're going to plug into that formula is the number 5, and you're going to plug in every integer between 1 and 5. So you're going to plug in n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. You continue to plug in all of the integers from the lower limit to the upper limit, and then we're going to take all those integers and add them together. That is what summation notation represents. So let's start with n equals 1. If I plug 1 in for n, I get 3 times 1 minus 2. The first term of the sequence is 1. And I'm adding that to when n equals 2. So now let's plug in n equals 2. I'm going to plug it in. I get 3 times 2 is 6. 6 minus 2 is 4. The next term of the sequence is 4. Then I plug in n equals 3. If I say n equals 3, I have 3 times 3 is 9. 9 minus 2 is 7. So the next term of the sequence is 7. Then I plug in n equals 4. If I do 3 times 4, that's going to give me 12. 12 minus 2 gives me 10. And the last term, which is the upper limit, is n equals 5. If I plug in 5 for n, I have 3 times 5 is 15. 15 minus 2 is 13. So I'm taking all of those terms in the sequence and adding them together. If I do that using my calculator, my sum is going to be the number 35. So the summation notation gave us an answer of 35 simply by using the rules that we had listed and the limits, all right? The limits are very important here because those are the numbers you're plugging in. All right, let's move on to the next part, which says in summation notation, the least and greatest integer values of index n are called the limits. And we talked about this a little bit when we just went over that example. The limits of this example, right, which is the same example that we saw above, are 1 and 5. The lower limit is n equals 1. The upper limit is n equals 5. Those are the two limits, and we're plugging in all the integers between those limits. All right, moving down, now we have the sum of an arithmetic sequence. So we're going to talk about some more formulas and how to use them. When a sub 1 is the first term of an arithmetic sequence, a sub n is the nth term, and n is the number of terms. Here are the formulas we're going to use when we're finding the sum of arithmetic sequences. So if we know what the first and last terms of this sequence are, so if we know what a sub 1 is and what the last term of the sequence are, we're going to use this formula to evaluate the sum of the sequence. S sub n equals n divided by 2 times a sub 1 plus a sub n. This is a formula you will be using on your homeworks and your test. Now, the second formula that we have is if a sub n is not known. So, for example, if we don't know how to find the nth term of the sequence, this is the formula we're going to have to use. We have S sub n is equal to n divided by 2 times 2 times a sub 1 plus n minus 1 times the common difference d. And again, this is the formula we use if we do not know what a sub n is equal to. All right, with that being said, let's move on to the next page where we are going to look a little bit more closely at summation notation. So like we said previously, the Greek letter sigma is used to indicate a sum. Use limits, the upper bound and the lower bound, to indicate how many terms you are adding together. Write the limits below and above the sigma symbol to show the first and last term of the series. So let's say we have the following summation notation, and I'm going to write this down a little bit bigger, and we're going to break it apart. So I have my sigma symbol. On the top of my sigma symbol, I have a 6. On the bottom, I have an n equals 2. And on the right-hand side, I have n squared. Here is what each of these components are referring to. So as we said before, n equals 2, that's referring to your starting value. Okay, that's the first number that you're going to plug into the formula. Then we have on the top, we have a 6. That represents your ending number, or the last number that you're plugging into the formula. The sigma symbol itself is telling you, hey, I am adding all of the numbers in this series together. And then the n squared is referred to as your explicit rule. All right, that's essentially the formula or the rule that you're plugging all of your integers into. So that is what everything represents. So if I were looking at how to write this, again, the first thing I'm plugging into the formula is 2. So the first term of my series is going to be, plug it into the formula, we have 2 to the second power. So that's the first thing I'm plugging in. Then I'm going to go from 2 up to 6, since those are my upper and lower bounds, and I'm going to plug in every integer between 2 and 6. So now let's plug in 3. If I plug 3 in, I'm going to have 3 squared. Plug in 4. I have 4 squared. Plug in 5. I have 5 squared. And last but not least, if I plug in that upper bound 6, I am going to get 6 squared. And I'm ending with 6 because that is my upper bound. All right, let's go ahead and evaluate these. Well, I know that 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So those are all the numbers I'm adding together. And then if I plug that into my calculator, my final answer is 90. So using this symbol right here, I got an answer of 90. All right? And that is how you deal with summation notation. All right, let's go ahead and jump into some examples. So starting with example number 1, we are going to find the sum of the first 100 natural numbers. Now, what do we know about the natural numbers? Well, back to unit 1, we talked about how natural numbers start with the number 1 and then go up 1 integer at a time up to positive infinity. Okay, so it's essentially the counting numbers, 1, 2, 3, 4, 5, 6, and so on. Now, if we're looking at the first 100 natural numbers, that means we know what the first term is. That's just going to be 1. And we also know what the last term is. If there are 100 natural numbers, the last term is going to be a sub 100, and that's just going to be the number 100. On the previous page, we listed a formula that we can use if we know the first term and the last term of a sequence, and we can easily use the formula to find the sum of the sequence. So this formula on the previous page is S sub n equals n over 2 times a sub 1 plus a sub n. Just keep in mind that n represents the number of terms in your sequence, a sub 1 is the first term of your sequence, and a sub n is the last term of your sequence. So we're just going to plug all this stuff in to find the sum. I get S sub n is equal to, well, again, since there's 100 of the natural numbers in this sequence, n is 100. That's the number of terms in the sequence. So we're going to have 100 divided by 2 times a sub 1 plus a sub n. That's going to be 1 plus 100, which was a sub 100. All right, so let's go ahead and do this problem. We're just going to simplify the inside of the parentheses first. I get S sub n is equal to 50 times 1 plus 100. That is 101. And then I know that 50 times 101 is going to give us S sub n equals 5,050. So what this means is the sum of the first 100 natural numbers, 1 through 100, is going to give you 5,050. Example number 2. Find the sum of the first 15 terms of the arithmetic series 2 plus 5 plus 8 plus 11 plus 14 plus 17. All right, so here's the issue. If I need to find the sum of the first 15 terms, I only have 6 terms listed in this series. So I do not know what the 15th term is going to be, so I can't use the formula I used before, all right? Because the formula before, I need to know what the first and the last term of the series is. So I'm going to have to use a different formula. So when we don't know, I'm going to say when we don't know a sub n, again, that is the last term of your series, we are going to use the second formula on the previous page, which is a little bit more involved, but it says a sub n, or excuse me, sorry, S sub n, all right, the sum of the series is equal to n over 2 times 2a sub 1 plus n minus 1 times d, and that is the formula that we use. So obviously we need to know 3 different things. We need to know n, the number of terms in the series, a sub 1, the first term of the series, and d, the common difference of the series. Well, we just so happen to have all 3 of those things. So let's go ahead and list them to the side here. A sub 1 is the first term of the series, which I know is 2. So I already know what one of those variables is. I also know what n is equal to. N is the number of terms in the series. That is 15 terms, because I'm looking at the first 15 of the series. And then I know that the common difference of the series is just whatever we're adding to get to the next term in the series. So to get from 2 to 5, I have to add 3. To get from 5 to 8, I have to add 3. 8 to 11, I'm adding 3. So my common difference amongst my terms is 3. So now we're just going to plug all of those things in. I have S sub n is equal to n over 2, or in our case, 15 over 2, times 2 times a sub 1, that's 2 times 2, plus n minus 1 times d. In our case, that's 15 minus 1 times 3. All right, so let's go ahead and simplify this a little bit. Well, 15 over 2, that's going to have to remain 15 over 2. We're not going to convert that to a decimal. 2 times 2 is 4. I know that 15 minus 1 is 14, and then 14 times 3, that's going to give me 42. So I have 4 plus 42. Now, 4 plus 42, that's going to give me 15 over 2 times 4 plus 42, that's going to give me 46. And what I can do now, since I'm multiplying a fraction by 46, the denominator, 2 and 46, we can pull a 2 out of 46 easily. So I can cancel out this denominator, and I get 15 times 46 divided by 2 is 23. And if we do our math here, 15 times 23, that is going to give me S sub n is equal to 345. Okay, so that is how you find the sum of a series if you don't know what the last term is equal to. On to the next page, example number 3. Find the sum of the finite arithmetic series 4 plus 9 plus 14 plus 19 plus 24 Ooh, we have a little missing spot right here, and then 99 at the end. Okay, so here is the struggle with this example. We know what the first term is. We know what the last term is. We know what the common difference D is, but unfortunately, we don't know what N is equal to. We have no idea how many terms are in this series, all right? This could go on for a long time. Now, obviously, we could continue to add whatever the common difference is to this number until we get to 99, but that would take forever. There's a more methodical approach that we could use using some of the formulas that we've been given previously. So for this example, you are not only going to need the formula that we used for the previous example, specifically example number 1, but you're also going to need the rule for an arithmetic series. Because if we know all of the components except for n, we could easily plug into the rule and we could figure out what n is equal to. I know that the rule for an arithmetic series is a sub n equals a sub 1 plus n minus 1 times the common difference d. Like I said, I already know what all of these things are equal to except for n. So let's go ahead and plug in what we know. Well, we know that a sub 1, the first term, is 4. All right, because that's the first term of the series. We know that a sub n, the last term, is 99. I also can figure out what the common difference is simply by seeing what I have to add to each number. To get from 4 to 9, I'm adding 5. To get from 9 to 14, I'm adding 5. And we know since this is an arithmetic series, each time we're going to be adding 5. The common difference d is equal to 5. So now I'm going to plug these into the rule and solve for n. Instead of a sub n, I'm going to put 99 is equal to a sub 1, or in our case 4, plus n minus 1 times the common difference, which we know is 5. So if we distribute this 5 into the parentheses and solve for n, here's what we get. 99 is equal to 4. That's going to be minus 5 plus 5n. Simplify that, we get 99 equals negative 1 plus 5n. All right, we add 1 to both sides. That's going to give us 100 equals 5n. And then if we divide both sides by 5, we're going to find that n is equal to 20. So now that we know what n is equal to, I now know that the first term of the series, a sub 1, is equal to 4. A sub n, or in our case, since there's 20 terms in the series, we just figured that out, a sub 20 is going to be the number 99. And I know that the n, or the number of terms, is equal to 20. Now I could plug this into the formula that I used for sum for example number 1. And the formula that we used was s sub n is equal to n over 2 times a1, a sub 1 times, plus a sub n, okay? So now we're just going to plug this stuff in. I know that s sub n now has to equal n over 2, which is 20 over 2, times a sub 1 plus a sub n, so the first term plus the last term. That's going to give me 4 plus 99. Then if I simplify this a little bit, I'm going to get 20 over 2. That gives me 10 times 4 plus 99. That is 103. Plug that into my calculator, and I find that s sub 20, or the sum of the series that has 20 terms, is going to be 10 times 103, which is 1,030. So this is my final answer. Example number 4, find the sum of the series. Ooh, this one is written in summation notation. We have this fancy sigma symbol. We know that our lower bound is 1, our upper bound is 13, and our formula is 4k plus 5. So what this is telling us is that the series starts by plugging 1 in for k, and then we plug in every integer from 1 to 13, and then we have to add those together to find the sum. So you're like, okay, Mr. Teal, for real? I'm going to plug in k equals 1 and then every integer between 1 and 13? Are you crazy? No, absolutely not. We are going to be using a more methodical approach to solve this problem. We are going to use the formula that we used for number 3. We just have to relate summation notation to this formula. So let's think about what we need in order to plug stuff into this formula. The first thing we need is we need to know what a sub 1, or our first term, is. We also need to know what our last term is, a sub n, but since we're talking about a series that has a lower bound of 1 and an upper bound of 13, we know that the last term of the series is going to be a sub 13, or the 13th term. And we also need to know what n is equal to. And like I said, if our lower bound is 1 and our upper bound is 13, that gives us n equals 13. There are 13 total terms, or 13 total things that we're going to be plugging in here. So in order to find a sub 1, what that means is I have to plug 1 in for k. So if I plug 1 in for k, I get 4 times 1. 4 times 1 is 4, and then 4 plus 5 is 9. So a sub 1 is equal to 9. I also need to find a sub 13, or the last term of the series. So let's plug in 13. 4 times 13, that's going to give me 52. And if I take 52 and add it to 5, a sub 13 gives me 57. So now I can easily plug this into the formula. We have s sub n is equal to n over 2 times a sub 1 plus a sub n. So let's plug it in. That means s sub, we have 13 terms, so s sub 13 is equal to n over 2, or 13 over 2, times a sub 1 plus a sub n, 9 plus 57. Let's simplify this a little bit. 13 over 2, we're going to keep that as a fraction. 9 plus 57, that's going to give me 66. Then we can obviously take 66 and divide it by the denominator 2, and we're going to be left with 13 times 33. 13 times 33, that's going to give me s sub 13, or the sum of this series is equal to 13 times 33, which is 429. All right, and that is how you find the sum of the series listed in summation notation. Example number 5. Now we're going to be shifting gears a little bit. We have a series, and what we need to do is we need to write the summation notation for that series. So let's start with part A. We have 3 plus 6 plus 9 plus 12 plus 15. Well, let's think about what we need in order to write something in summation notation. We know that we need to know what the lower limit is equal to, or the lower bound. We need to know what the upper bound is equal to, or the last thing that we plug in. And we also need to know what the formula is for the series, okay? So what are we plugging this lower bound and this upper bound and everything in between into, okay? So let's go ahead and figure out how to do that. Well, first of all, I can easily find what my upper and lower bounds are, because the lower bound is the first thing you're plugging in. And remember, the first term of an arithmetic series is a sub 1, so the lower bound is going to be 1. We know that the last term of this series, since there are 5 terms of this series, is going to be a sub 5. So the last thing we're plugging into this formula is 5. So the upper bound would equal 5, the lower bound would equal 1. But we need to figure out what the formula for this summation notation is going to be. And the way we're going to do that is we're going to use the rule for an arithmetic series, because we know that arithmetic series, their rules, give us something that we can plug n values into and get out whatever the term is going to be in the series. And that is exactly what we need when we are figuring out what each individual term is equal to using summation notation. So I'm going to set up my arithmetic rule, and that's going to be the formula I use for summation notation. Now, the formula for the rule of an arithmetic series is a sub n equals a sub 1 plus n minus 1 times d. And we learned this in the lesson where we talked about arithmetic series. All right, so what we know here is we know that a sub 1 is equal to 3. We know that the common difference d can easily be found by seeing what we're adding each time. And we can clearly see that we're adding 3 to get to each term in this series. So the common difference is 3. And we're not going to plug anything in for n, because again, n is the thing that we're plugging stuff into, okay, because we're creating a formula, and that is going to give us what the terms are of our series. So we're just going to plug in a sub 1 and d to create our rule. Well, we will find that a sub n equals a sub 1 is 3, plus n minus 1 times the common difference d, which we said was 3. Then if we distribute and clean this up a little bit, I will find that I have 3 times negative 1 and 3 times n. That's going to be 3n minus 3. The positive 3 and the negative 3 would cancel, so we're just left with a sub n equals 3n. So the rule for the arithmetic series is 3n. This is what I'm going to use for my formula in summation notation. Like I said before, I know that my upper bound is going to be equal to 5 because I have 5 terms in my sequence. And my lower bound is the term that I'm starting with. My lower bound is 1. All right? So if I'm going to plug this into summation notation, I have the sigma symbol. The top of the symbol is going to be 5, the upper bound. Lower symbol, we have to include our variable. Since we're talking about n's here, I'm going to say n equals 1. And the formula I'm using, or the arithmetic rule, is 3n. And this is my answer. Next page, we have example number 6. Now we are looking at series and summation. If an arithmetic series has a sub 1 is 2, d is 5, and n is 20, we need to first write the summation notation for the series. Well, once again, the things that we need to write summation notation are the lower bound, the upper bound, and the rule, okay? So what we're going to do first is let's figure out what the rule is using the rule of an arithmetic series. So we know that the rule of an arithmetic series is the formula a sub n equals a sub 1 plus n minus 1 times the common difference d. And we can plug all these things in based on what we have above. Again, though, you are finding the rules, so we are going to leave n alone because that's what we're plugging values into to figure out the individual terms of the series. So we're going to plug in everything except for n. We get a sub n is equal to, a sub 1 is 2, so I say 2 plus n minus 1. Again, leave n alone because we're plugging stuff into that for the formula. And d is 5. Well, if I distribute this and clean it up a little bit, I have 5 times n is 5n, 5 times negative 1 is negative 5. So we're going to get a sub n equals 5n. Negative 5 plus 2 is going to give me negative 3. This is the rule of the summation notation, okay? So this is what I call the rule. Now, let's go ahead and write down the summation notation. I need to know what my bounds are. My lower bound is just going to be 1 because that's the first number that I'm plugging into the rule. So I'm going to say n equals 1. And since there are 20 terms, or n is 20, there are 20 terms in this series, my upper bound is 20. And my rule, I'm just going to write down as 5n minus 3, and this is the summation notation for the series. Now, part B, we need to find the sum of the series. And we know that the formula for the sum of a series is S sub n equals n over 2 times a sub 1 plus a sub n. We know what the first term is. We know what the last term is. So we can easily plug those into the formula. Well, I know that n is the first thing I'm plugging in, and n is equal to 20. That's given above. I know that a sub 1, that's the first term, and we already are given that. That's 2. So a sub 1 is 2. And then a sub 20, we could easily find that simply by plugging 20 in to the rule. So we'll say 5 times 20 minus 3. 5 times 20, that's going to give you 100 minus 3. So we find that a sub 20 is going to give us 97. So let's plug those into the formula and figure out what our sum is. The sum of this series, which actually is going to be s sub 20 because n is equal to 20, that gives us n over 2, which is 20 over 2, times a sub 1, 2, plus a sub n, or the last term of the series. That gives me 97. So let's clean up those parentheses. I have 20 over 2. That gives me 10. And then 2 plus 97, that is 99. And if I take 10 and multiply it to 99, I find that the sum of the series is equal to 990. That's my final answer. Okay, Mr. Teal, but what about word problems? Example number 7. How many logs will be in a pile of timbered trees if there are 30 logs in the bottom layer, 29 in the second, and so on until there is 1 in the top layer? All right, well, we need to find how many logs will be in the total pile. So in other words, we need to find the sum of 30 plus 29 plus 28 plus 27 plus 26, and so on until we get down to 1. So I'm going to have to use the formula S sub n is equal to n over 2 times a sub 1 plus a sub n. But in order to do so, I need to figure out what each of these things is equal to. Okay, well, first of all, if I am starting with 30 logs, That tells me that a sub 1, the first term of the series, is 30. All right? I also need to know what a sub n is. That's the last term of the entire series, and that's going to give me 1, because the last row has to have 1 log. And then I need to find what n is equal to. Well, to get from the first term down to the last term, this is going to take 30 different rounds. So I'm going to say n equals 30, okay? Because that's the number of terms there will be in the series from 30 down to 1. So let's go ahead and plug all of those into the formula. We have s sub n is equal to n over 2, which is 30 over 2, times a sub 1, 30, plus a sub n, that should actually be a sub 30, because that'll be the 30th term. But in any case, a sub n, that's going to be the last term, which is 1. So let's do the math here. We have 30 divided by 2, that gives me 15. 30 plus 1 is 31. And we find that 15 times 31 is going to tell us that s sub 30, or the sum of this series, gives us 465. Since we're talking about logs, my unit is logs. And this is my final answer. All right, number 8, this is just a quick bit on how to use the calculator to find the sum of a series. So for example, if you wanted to find the sum of this summation notation, all you would have to do is on your calculator, go to Math 0, that's the summation button, and notice how it has the sigma symbol. And then we can literally just plug in all of the individual components to the symbol. And if we plug that into our calculator and click enter, we get 432. Obviously, since we're not on campus, I'm not going to focus as much on this one, but if you wanted an extra way to check your work and you have a TI-84, this is how you would use the TI-84 to evaluate the sum. All right, you guys, and that is the last example for today, so I hope you guys have a great day, and if you have any questions, please let us know. Bye, guys. See you next time.